Right, now today we're going to be looking at section 3.2, which is going to be our introduction into functions. Our introduction to functions. Functions, it's kind of a fancy way of looking at things, but um, these are incredibly important. We're going to be working with these throughout the entire semester, the whole course. College algebra deals a lot with functions as well. So the question you have is, what is a function? A function is used to describe a relationship between two quantities. Okay, so mathematically, it's a set of ordered pairs or points. Remember, anytime we see ordered pairs, we think points in which no two ordered pairs have the same first coordinate. The domain. So we're gonna work on examples that deal with all of these. So just bear that in mind. The domain is the set of all the x values, while the range is the set of all the y values. So I kind of write a little note here and I say the book really complicates this definition, so let me make it as simple as I possibly can. Functions can represent basically anything. They can be graphs, tables, equations, anything like that, but the important part is that they do not have duplicated x values. You cannot have multiple x values represented in your function. Okay, so for example, when I ask you what's the domain and the range of the following relation and is the relation a function, here I'm giving you a set of coordinates. Okay, this is an x value and a y value. So here's one x value and y value, here's another one, so there's what, 1, 2, 3, 4, 5, 6 different points here. When we're looking for the domain is just going to be the x values. So 2, 3, 4, 5. We already counted 4, so we don't need to put it twice. And then 6. So it's just the x values which are the domain. The range is going to be just the y values. So 4, 6, 8, 10, and then 6 and 10, these are duplicates, so we don't need to rewrite them. Okay? So the range is the set of y values. Domain is the set of x values. The range is the set of y values. This relation that we see right here is not a function, and the reason why is because if you look at the x values, you notice how there's a 4 here and a 4 here. Because they're duplicated and I have a 4 in 2 different places, this is not a function. Okay? If, for example, this guy right here was a 7, then it would be a function, because each of these x values are completely distinct. None of them cross over, none of them overlap. I'm not repeating any of those x values, so that would be why it would be a function. However, it's not. This is not a function. The book actually has a few different ways to represent using some Venn diagrams. You can take a look at them on page 122 just to see a few examples, so we really encourage you to go ahead and do that. Jump into the textbook and just see how they show you a few things. There are some other terms that we do need to keep in mind when we're looking at equations. So when I say y is equal to x squared, the y variable is called the dependent variable. Usually the dependent variable is always going to be what your equation equals, like on the left-hand side, or I should say it's the thing that's like dependent. I know that sounds really stupid because that's the definition, but the reason why we say dependent because it depends on x. The x variable is going to be called the independent variable, right? It can change, it can move, it can be whatever it wants, but in this case, y depends on whatever x is going to be. Okay? So in this case, the way that we say it is y is a function of x. So notice, this says y is equal to x squared. Now there's a different way that we write this in math. We can also write it, so this is like an equation that you're used to seeing, where it's y is equal to x squared. But function notation just changes it up to look a little differently. What this says is a function of x, which you can think of as y is equal to f of x. A function of x, f of x, is equal to x squared. So literally speaking, these two things, the equation right here, y is equal to x squared, and then f of x is equal to x squared, these are the same thing. It's just a different way of writing it. So you're probably wondering, why in the world would we ever write it like this? It seems like it's more complicated. Yes and no. In some sense it is, but for the most part it actually does make things a little bit more simple. And I'll explain why when we start to go through some examples below. Specifically, when we get to the point of evaluating functions, what we're doing is we're substituting values for x to solve for our y value. So we're finding a y value, but it just looks a little different. So if I want to evaluate the function at x is equal to 3, what that's saying is that I'm trying to find a corresponding y value. So let's, for example, imagine x is equal to 3. I'll go ahead and substitute it into the first example. So y is equal to x squared. I get y is equal to 3 squared because I'm making that substitution. Well, what happens? That means that y is equal to 9, right? Because 3 squared is just 9. However, if I'm using function notation, what I'm doing is I'm replacing the x with a 3. I'm replacing the x with a 3. So f of 3 is equal to 3 squared. And that means, again, I'm just carrying this along for the ride, just like we did here in the first one. Y equals 3 squared, which means y is equal to 9. F of 3 equals 3 squared, which means f of 3 is equal to 9. Okay, it means exactly the same thing. Again, it's just a different way of writing it. Now, the beauty and the benefit of writing it this second way is that notice in the solution, here I have both my x value and my y value. F of 3 is equal to 9. So that means the point is going to be 3, 9. So you're kind of using the 3 as like your reference for your solution. That's kind of a nice way about writing this. And personally, I prefer writing it this way. Once you get used to it, it makes a lot of sense. And again, we'll go through some examples so you can see. Again, I kind of explain what I just explained here in this last paragraph, but you can see why it's beneficial to write it like this, because I know what the x value is, and then I know what the y value is. When we graph functions, the graph of the function is the graph of the points that belong to the function. I mean, I think that's kind of obvious. We did an example in the last section where that was the case. So you can go ahead and go back and look at that. We'll probably do some more here in the next few lessons. I'm not sure if I'll get to one in this lesson, but hopefully you'll see. And then lastly, I want to talk a little bit about the vertical line test. The vertical line test. So again, because we're talking about functions, functions have a very specific definition. Remember, we can't have any duplicate x values. They have to all be unique and distinct. So a simple trick to determine if any graph is a function is to imagine you're drawing straight vertical lines through each point on the graph. The trick is that if the vertical line test, or essentially if it fails the vertical line test, it will cross the graph at multiple points. It won't just be one point. So this top one is not a function because you can see how the graph, if you trace it, it actually kind of curls back on itself. And if I draw a straight line through those red points right there, then I have a line that crosses the graph at multiple points. That actually means that it's not a function. So that's something to really keep in mind, okay? If you see something like this, or for example, if I were to draw a circle is a graph, but if I draw a vertical line through the circle, you'll see that the vertical line touches the graph at most 2 points. And I can't, that means it's not a function. The vertical line test means that every vertical line that I draw can only touch the graph once. It cannot touch more than one time. Okay, so it's just a unique little trick just to test whether or not you have a function. This is something that will show back up if you go to college algebra after this course. So just keep that in mind as we go through. Okay, so that's a lot. Introduction to functions. Again, this is kind of a radical or different way of thinking about how we represent and write down our equations. So what I'm going to do is I'm going to bring up the whiteboard. Let me bring up my program here real quick. My camera turned off. Sometimes if I leave it on for too long, the program freaks out a little bit. I'm not sure why that's the case, but let me go ahead and flip over to my whiteboard. And what we're going to do is we're going to go through a few problems. So 3.2, question number 6. This is actually a similar question to what we left the last one. So what number is not in the domain of f of x? Again, you can think of f of x as the same as y. It's just a different way of writing it. X over x minus 2. So again, the trick here is look at the denominator. Okay. Take a look at the denominator. And when the denominator equals 0, that x value is not in the domain. So when the denominator, I'm going to shorthand it and say denom, the denominator equals 0, the x value we get when we solve is not in the domain. Okay, so what we do is, again, we take this denominator and we paradoxically set it equal to 0. You're like, wait, we don't want that to be 0. You're right. But in order for us to find what's not in the domain, we actually have to set it equal to 0. You could do this if you want, say not equal to 0, but I just like saying equal to 0. It's fine. So now we add 2 to both sides, and in this case, I'm going to find that x is equal to 2. Okay? So x equals 2 is not in the domain. So that's one of the problems that we'll come across, especially when we deal with rational functions. In other words, where it's one function divided by another one. What happens is that we need to take into account just a few minor things. So x minus 2 means that x equals 2, which is the value that will cause this thing to be 0, cannot be in our domain. Okay, so that's how you go about solving one of those problems. Let's go ahead and solve, let's go to question 16. So here they actually give us a, similar to the example that I gave in the notes, it's a bunch of different points. 2, minus 2, 4, 2, 4, and minus 2, 5, 4, 9. Okay, so these are all of our points. This is our set that we're dealing with. And so they're asking us to find the domain, the range, and whether or not this is a function. So the domain, what I'm going to do is find all the x values. So -1, -2. A lot of times they'll ask you to put it in order, but I don't really care as long as you can represent it. Looks like -2 shows up twice, so we ignore that, and then we're going to move on to 4, and there is our domain. Now the range is going to be all the y values. So 2, 4, 4, we already got that, 5, and 9. Okay, so that is going to be our range. The question is this a function? Is this a function? And the answer, again, depends on whether or not we have any duplicate just x values, okay? You can have as many duplicate y values as you want. It doesn't matter. That's another specific type of function. However, this right here is what we're looking at. We're looking at just the x values. So there's a -1, a -2, a 2, a -2. Notice how the -2 here and the -2 here, there are 2 of them. That means that this is not a function. Okay? And the reason why is we cannot have duplicates. Cannot have duplicate x values. If we have duplicate x values, we do not have a function. Okay? Now what I want to do is I want to show you some evaluation. So we all have done this, but we're just going to change the way that we write it to look like a function instead. So 34, this says evaluate p of z, so a function of z, which is equal to 4 minus 6z. Okay, and then I'm going to do another one after this one so you can see how that works. All right, so now we're evaluating the function for there's 3 parts of these questions. Part A is asking us to evaluate p of 2/3. Part B is saying p of 4. And part C, I'm hoping I have enough space here, p of minus 5/6. Okay. We'll start at the top here. P of 2/3. So what is this saying? This right here is a z value, okay? Which means that every single place we see a z in this equation, we're going to change it with a 2/3. So that means that I have 4 minus 6, and the z is going to become a 2/3. Okay? So p of z is equal to 4 minus 6z. The same thing here, p of 2/3 equals 4 minus 6 times 2/3. So let's go ahead and work these out. 4 minus, so 6 times 2 is going to be 12 over 3. And this is going to be 4 minus 12 divided by 3 is going to be 4, which is equal to 0. Okay, so take a look at what we have. P of 2/3 is equal to 0. So in other words, the point that we can think about this as is going to be 2/3, 0. You can think of this as like an x value and a y value. Okay? We'll do, again, we're going to go through these, and then I'll do a couple of other examples so you can see how this all works. 4 minus 6 times 4, again, I'm evaluating at z is equal to 4, which means this guy is going to turn into a 4. So this means that I've got 4 minus 6 times 4 is going to be 24, which is a minus 20. So the point, I'm going to combine the front and the back so you can see what it looks like, minus 20, right? There you go. This means that my point is going to be 4 minus 20. Okay? Let's go ahead and do this next one. So we've got 4 minus 6 times, remember that's our z value, minus 5 over 6. Now here's the cool thing. I've got 2 minus signs. I'm going to do a little bit of mental math on you here. I'm going to skip some steps. If you want to go back and work this out on your own, you certainly can. But I'm going to do some mental math and kind of go fast. This 6 cancels with that 6. This plus becomes that. So I'm actually doing 4 plus 5, okay? Because the 5 is remaining, these become positive because there were 2 negative signs, so therefore I get 4 plus 5 is equal to 9. So in other words, P of minus 5/6 is equal to 9, and as a point I can represent this as minus 5/6, 9. So that is how you'd go about solving question number 34. All right, let's move on. We're going to up the stakes a bit. Or the difficulty. 48, r of s is equal to 3 minus 6s minus 3s squared, okay? So a little trickier. We have a square in there. So let's just go one at a time. I might have to erase because these might have to work out a little bit more. The first one they ask us to solve is r of minus 2. So that means that everywhere I see an s in my equation, I'm going to replace it with a minus 2. So 3 minus 6 times minus 2. You can see the substitution there. Minus 3 times minus 2 squared. So this right here is the same as 3. We're just going to work this out. Minus 6 times minus 2 is going to be a plus 12. Minus 3. Minus 2 squared is going to be a 4. Okay? So then I've got 3 plus 12, that's 15. Minus 3 times 4 is... I'm kind of breaking the order of operations a little bit. Part of the reason why, though, is because I'm only combining things that I know will combine in the end. So I'm kind of taking a little bit of a shortcut here just to get down to the solution. You can use order of operations on all of this stuff, but trust me, I know what I'm doing. So 3 times 4 is going to be a minus 12, so this is equal to a 3. Okay. So in other words, if we're looking at r of minus 2 is equal to 3, and that means that the point that we have is minus 2, 3. Okay? If you wanted to go the order of operations way, you would do the exponent first, so it would be minus 3 times 4. Then you would do the multiplication. So minus 3 times 4 is going to be a minus 12. This then would be a plus 12. That would be a 3. So you can kind of see it's all going to work out to be exactly the same. All right, 48. That was 48 right there. Oh, you know what? Shoot. I got to rewrite that out because there were 2 other parts of that problem that I want to go through. 3 minus 6s minus 3s squared. Okay, so part B. R of minus 2/3 is equal to, so now we make the substitution. Everywhere we see an s, we substitute minus 2/3. 3 minus 6 times minus 2/3 minus 3 times minus 2/3 squared. I think I will use order of operations on this one because it is a little trickier with all these fractions. All right, so please excuse my dear Aunt Sally. Parentheses, we don't have any of those. We do have exponents, so let's go ahead and do those first. Minus 2/3 minus 3 times 2/3. Negative 2/3 to the second power is the same as 4/9. The minus signs, they get wiped out by squaring it, so we don't have to really worry about those. Okay, so now we did the exponents. We're at multiplication division. Let's go ahead and do that. 3 minus and a minus is going to turn into a plus, and this is going to be a 12/3 minus 12/9. How about that? Okay, but now we've got a whole bunch of fractions. Yay, we love fractions. They're amazing. What I'm going to do is, actually, we can simplify this first. Let's just do that. 3 plus 12/3 is just 4, and that makes our lives a lot easier. 12/9. This is the same thing as 7 minus 12/9. Now, when we find common denominators, it's a lot easier. So imagine I have, so 12/9, we're going to be using 9 as our denominator, which means that I'm going to multiply 7 times 9/9. This is the same thing as 1 minus 12/9. So this is the same as 9 times 7 is what, 63? 63/9 minus 12/9 is equal to, oh boy, 51/9. And you can reduce that even further down to 17/3. Okay. That took a lot of work, obviously, to get down there. You can use a device to help you out, but again, that was just me trying to work it out for you so you could see. Because I went a little fast on the last one, I'll admit. So, all right, so r of minus 2/3 is equal to 17/3. This is equal, which means the point is going to be minus 2/3, 17/3. Okay? So that's our x value, that's our y value. And that's part B. Now, surprisingly, part C is actually a little bit easier than that last one because it really doesn't require any arithmetic. Let me show you what they ask us to do in part C. Part C, they say find r of minus x. Well, how do we do that? It's a variable. We're swapping a variable with a variable. What? You can do that. So remember, everywhere you see an s, you substitute it with whatever is in your parentheses here, minus x. So 3 minus 6 times minus x minus, sorry, that's a 3, minus x squared. Okay? Now to simplify this, let's just multiply all this out. Minus 6 times a minus x is going to be a plus 6x. Minus x squared is going to be just x squared because the minuses are going to cancel. So this becomes a minus 3x squared. And there it is. That's our solution. So you're probably like, wait, how does that work? This is not a point. Well, sometimes when we have functions, we're substituting other functions into our functions. There's a lot of reasons why we do that. When we get into college algebra, we'll talk a lot more about why we would do something like that. But in general, there's a lot of different reasons why. One reason in particular, I'll just kind of spitball this off the top of my head, is imagine you own a business and you have a specific equation that kind of charts out your a specific amount of inventory, how much profit you generate from inventory, but then you want to look at your total business profit in terms of the profit from that one piece of inventory. That would be why you would make this substitution. It sounds really complicated, but this happens quite often in a lot of different situations. So that's question 48. I've got one more question, and then we're going to jump. And then we'll be done. Actually, that's going to be the end of this content. So question 58. R of s is equal to s cubed minus 2s squared minus 5s plus 2. And they're asking us to evaluate when s is equal to a minus 3. So what that means is I'm looking for r of minus 3. Remember, s is minus 3, so I'm looking for r of minus 3. So minus 3 cubed minus 2 times minus 3 squared minus 5 times minus 3 plus 2. Again, I'm going to do some mental math here, so try to follow along, and if I'm going too fast, then just slow the video down to the appropriate speed. We're looking at minus 3 cubed. So 3 cubed is going to be 3 times 3, which is 9, which is 3 times 3, which is 27. Since there's a minus in front and the minus is multiplied 3 times, it's going to stay minus. So this is going to be a minus 27. Minus 3 squared is going to be a 9. 9 times 2 is going to be 18. The minus sign will still come along for the ride. Minus 5 times minus 3 is going to be a plus 15, because there's 2 minus signs. And then I'm adding 2. All right. Can I do this in my head? Well, here, let me pull this down so you can maybe see it. Sorry if you can't. When you deal with a lot of adding and arithmetic like this, usually I try to go in and I try to find things that are a little bit more simple to work with and then combine them up. Like, for example, minus 18 and a plus 15. If I just look at this part, I know that the difference between those is going to be a minus 3. Then I have, so this becomes minus 3, plus 2 is going to be a minus 1, so all of these go away. Minus 1 minus 27 is a minus 28. Okay, that's kind of how I think through these problems. So that right there is our answer. So in other words, r of minus 3 is equal to minus 28. And again, if we wanted to represent this as a point, we would do minus 3 minus 28. Okay, so here's our x value, here's our y value, or I should say this is our s value, and this is our r of s value. Okay, that's it for functions. There's a lot more cool stuff that you can do with functions. We'll get into that as we go through the semester, but that's pretty much the introduction. If anyone has any questions, again, like I said, don't hesitate to let me know. Thank you.